The history of math is our intellectual foundation to understanding science. Science. Beautiful, awesome, wonderful science. It's the creative foundation to our ineffable future. Hi, I'm Gabrielle Burchak, and this is my podcast, Math, Science, History. I often promote my website, mathsciencehistory.com. Of all the hosts that I've been with, my experience with Bluehost has been the best. What I really like about Bluehost is their customer service. It is top-notch. You can access Bluehost through my affiliate link, www.bluehost.com/track/mathsciencehistory, all one word. It's only $3.95 a month if you sign up for 36 months. So if you do the math, it's $142 to start. And for me, it was the smartest business investment I've ever made. Albert Einstein once said, "Two things are infinite, the universe and human stupidity, and I'm not sure about the universe." This quote leads me to wonder many things. 1. Will we ever evolve into intelligent beings? 2. Is the universe really infinite? And 3. What is infinity? For sake of brevity, I'm going to address the third question. Well, infinity has been around for forever, pun intended. But let's start with the basic definition. Infinity is not a number. So if you were thinking I was going to have a podcast where I would count to infinity, that's not going to happen. It could be fun, but then again, maybe not. Infinity is a concept, and it's this idea that infinity is larger than any number you can think of. It's also smaller than any number that you can think of. In both cases, they go on forever and ever without end. In other words, they are unbounded. In a small nutshell, a cardinal number is a number where one stops counting. Infinity with cardinals is infinity with numbers, so we count up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, blah, 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 blah. The thing is that we can't actually count to infinity. As a result, it's a concept, much like its smallest infinity, which is also known as an Aleph null. Aleph null is the very first cardinal number in a series of cardinal numbers. It's spelled A-L-E-P-H, Aleph null, N-U-L-L. Then we have infinities with ordinals. Ordinals allow us to arrange a collection of sets. So I could have a set of 3 shoes, a set of 7 socks, and a set of 1 pair of underwear. If I wanted to put them in order, hence the term ordinal, I would say, first, I have a pair of underwear. Second, I have 3 shoes. Third, I have 7 socks. What I love about this set that I wrote is that a pair of underwear is really only 1 underwear. 3 socks means you are missing a shoe, and 7 socks means that you only have clean socks for 3 days, and the third sock sits in the drawer for an infinite amount of time. The thing about ordinals is that they have a wide variety of different sets, and some of these ordinals hold sets with bigger countable numbers, like infinity to the power of infinity. Once they reach that size, they are uncountable. As a result, ordinals are bigger than cardinals are. There are other types of infinite numbers that can be used in various areas of mathematics. These include Bethe numbers, superreals, which are used in field theory, surreals, which are used in game theory, supercomplex, and others. In calculus, we work with infinity in such a way that we take things to the limit. Infinity is a concept that goes back to as early as 450 BCE, when Zeno of Elea presented his paradox that includes repeated division by 2. It means that if you divide a whole into a half, and then divide that half into another half, and then divide that half into another half, and then divide that half into yet another half, you have infinite halves. Sometimes I feel this way about a goal, and I'm sure some of you can relate. You know, when you want to accomplish something and it feels like the distance between where you're at and where you want to be is just a never-ending path of infinite halves. That's one way of relating to Zeno's paradox. Then in 350 BCE, during Aristotle's time, Aristotle believed that there were aspects of the world that utilized the concept of apeiron. It's spelled A-P-E-I-R-O-N, apeiron. It's a Greek word that means unbounded, like infinity. The Greeks considered apeiron as a bad word, as it alluded to the concept of chaos. A crumbled piece of paper was an apeiron. Jagged edges described an apeiron. But Out of chaos came order, and so Aristotle believed that the set of natural numbers could be potentially infinite. After Aristotle, this concept of infinity was used sporadically. Then, in the 3rd century, a Neoplatonic philosopher by the name of Plotinus developed a philosophy that presented the concept of an infinite God, also known as the One. This God could think infinite thoughts. What is interesting about this is that Plotinus was a Neoplatonic philosopher whose theories were foundational to academic paganism, which was a philosophy that Theon and his daughter Hypatia taught. Paganism was considered repugnant and disgusting to the church. However, 200 years after Plotinus, Augustine, who was eventually canonized as a saint, incorporated the philosophy of Plotinus into his teachings. Thus, Augustine preached that God was infinite and God could think infinite thoughts. So now we enter into the medieval age, where this concept of a number is part of spiritual teachings. It wasn't until around the time of 1200 that infinity became a mathematical concept. Enter Fibonacci, also known as Leonardo of Pisa. Fibonacci proposed a sequence of numbers created by adding the 2 numbers before it. So the sequence starts 0, 1, 1, 2, 3, 5. The next number is 8, since 5 plus 3 equals 8. The next number is 13, since 8 plus 5 equals 13. And so the sequence goes 0, 1, 1, 2, 3, 5, 8, 13, etc., 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 all the way up to infinity. And what's cool about the Fibonacci sequence is that it can be visualized. When you take these values and make them the length and the width of a square, position the squares next to each other, and then draw a curve, you get the Fibonacci spiral. And what's cool about this spiral is that it is a mathematical representation in nature. You can see the Fibonacci spiral in plants, in our galaxies, in the swirl of water. It's everywhere, and it's beautiful. I will post the images and the mathematical explanation on my website at mathsciencehistory.com for further explanation. Once we entered the Middle Ages, the concept of infinity was used on many different applications, specifically the division of fractions. In the 16th century, Raphael Bombelli utilized the concept of infinity while also addressing the problem with imaginary numbers. He presented this in the square root of 13, where he found the value by continually adding divided fractions. I'll post the mathematics on my blog at mathsciencehistory.com for further explanation and for a visual. By the 17th century, Galileo Galilei was using finite reasoning on infinite things. Galileo stated, quote, "This is one of the difficulties which arise when we attempt, with our finite minds, to discuss the infinite, assigning to it those properties which we give to the finite and limited. But this, I think, is wrong, for we cannot speak of infinite quantities as being the one greater or less than or equal to another." Unquote. Galileo then presented his paradox, which shows that the list of perfect squares is as infinite as a list of numbers. As a result, for the list of perfect squares, we have 1, which is 1 squared, 4, which is 2 squared, 9, which is 3 squared, 16, which is 4 squared, 25, 36, 49, 56, 81, and on and on and on. As a result, he showed that we cannot apply the concepts of equal, greater, and less than to the infinite. Those concepts can only be applied to finite quantities. However, this was the challenge. He had showed that an infinite list of squared numbers is larger than an infinite list of non-squared numbers. And so he grappled with how to show that some infinite sets are larger than other infinite sets. He couldn't do it. This task actually wasn't accomplished until about 250 years later through the genius of Georg Cantor. Georg Cantor was born in 1845 in Russia. He was an exceptional violinist and a brilliant mathematician. And though he was born in Russia, he was a prominent German mathematician. Many of his peers and contemporaries thought he was crazy because he came up with this concept of set theory. It's actually now a really valuable foundational fundamental tool used in mathematics. But for Cantor, who first proposed it, he was ridiculed and insulted. Cantor proposed that there are different different types of infinity. He proposed cardinal and ordinal numbers, and he showed a one-to-one correspondence between two different types of sets. In his theorem, he implied the existence of an infinity of infinities. This concept led to his idea that there are transfinite numbers. Transfinite numbers are numbers that are infinite in such a way that they are larger than finite numbers. However, they are not absolutely infinite. He was a genius with original ideas, much like Einstein. Sadly, he was rebuked by his contemporaries. Henry Poincaré, Leopold Kronecker, and others described him as a, quote, scientific charlatan, unquote. Kronecker went so far as to verbalize that he was uncomfortable working with Cantor, and even intentionally delayed the release of Cantor's first publication. Every time Cantor would apply to work at the University of Berlin, the university would reject his application. Many believed that Kronecker had a say in these rejections. In other words, Kronecker was being a real jerk. Cantor remained at the University of Halle, where he worked during his entire career and made a modest income. Cantor's contemporaries even accused him of corrupting the youth with his crazy ideas. Ludwig Wittgenstein even went so far as to say that his theories were laughable and wrong and complete utter nonsense. They were being unnecessarily brutal. Cantor began to struggle with ongoing bouts of depression. In 1884, he entered a sanatorium. It was believed that he might have had bipolar disorder. As a result, his depression worsened as his peers continually mocked him. On December 16, 1899, while Cantor was giving a lecture on his views on Baconian theory and William Shakespeare, Cantor's 12-year-old son, Rudolph, died unexpectedly. This was a devastating turn of events for Cantor. He lost his passion for life and his work. In 1903, he entered the sanatorium again for depression. Even after this, his contemporaries continued to mock him. However, he had also received many honors for his work. In 1904, the Royal Society awarded Cantor with the Sylvester Medal, which is the highest honor for work in mathematics. As Cantor's critics continued to vilify his work, David Hilbert came to Cantor's defense, stating, quote, "From his paradise that Cantor with us unfolded, we hold our breath in awe, knowing we shall not be expelled," unquote. However, that same year, in 1904, Julius Koenig presented a paper at the Third International Congress of Mathematicians where he tried to prove that transfinite set theory was completely false. Koenig read the paper in front of Cantor's daughters and colleagues, which devastated Cantor. Even though Koenig's proof of Cantor's work failed, Cantor was still distressed and continued to struggle emotionally. By 1913, he was poor and malnourished. By 1917, he entered the sanatorium again. He had continually asked his wife if he could go home. However, she wouldn't allow him to return. Then, on January 6th, 1918, he had a heart attack and died. It is a horribly sad ending for such a brilliant man who created fortifying foundations to set theory. The concept of infinity can be applied to so many areas today. One of the best explanations I've heard for infinity in physics comes from Hakeem Oluseyi in his TED Talk, which I will post on my website. In his talk, he describes an electron traveling through space. That electron can spontaneously become two photons, which can then spontaneously become a matter and an antimatter particle, which can then spontaneously become an ongoing infinite sum of subatomic particles. This is infinity at its most tangible. To quote Einstein again, he once said that imagination is more important than knowledge. Because of imagination, in the last 100 years, we have made technological leaps that we never could have accomplished in the 19th century. So, if we were to add imagination to infinity, consider all the infinite possibilities we could obtain. Imagine all the infinite possibilities for our mathematical advancements. Imagine all the infinite possibilities for our scientific advancements. Imagine all the possibilities in advancements for humanitarianism. I would like to hope that if we can imagine it, we can achieve it. But, like Zeno's paradox, it may take forever to get from here to there. I'm Gabrielle Birchak. This podcast has been brought to you by caffeine. Delicious, wonderful nectar of the gods caffeine. Coffee, tea, coffee candy, You name it. I love it. Thank you for listening to Math, Science, History. If you like what you are listening to, please remember to subscribe and leave a review. I would really appreciate that. If you are interested in reading more about the history of math and science, please come visit me at mathsciencehistory.com. And while you are there, if you like what you're listening to, please feel free to click on that coffee button and buy me a cup of coffee. Until next week, carpe diem.